All right, guys, I'm going to start. I have a bunch of slides. I don't know how much I'm going to be able to do, so let's get started. So today we're going to continue discussing the legacy of Turing, but we have actually another hero in this lecture, and that's Cantor. Cantor is considered to be the father of set theory, and if you remember, I think this was from third lecture, set theory is like the foundation of mathematics, right? So these ZFC axioms, the set theoretical axioms, the 9 axioms, basically, experience shows that almost all true statements that you can prove, like in the Gorm sense, like good old regular math, can be deduced from these axioms. Okay, so set theory is like the foundation of mathematics, and Cantor is like the father of set theory, and we know Alan Turing is like the father of computer science, so really it doesn't get better than this. Okay, so we're going to be talking about the ideas of these two great minds. Now, sadly, they sort of both had tragic lives. Cantor, for example, spent a significant portion of his life in a mental institution. And Turing, as you probably know, committed suicide when he was like 41 years old. So maybe if you don't know the story, let me quickly tell you the story about that. So Turing was homosexual, and at the time that was illegal in England. One day, Turing's apartment gets robbed. He calls the police. The police ask him, do you have any idea who might have done this? He says, well, it might have been my ex-boyfriend. They say, your ex-boyfriend, and they prosecute him. They give him an option of either going to jail or taking medication to cure his condition. Of course, he chooses to take medication. The medication makes him sick. He cannot work anymore, so he decides to commit suicide. He's a big fan of Snow White, so he injects an apple with a poison, and he eats it, and that's the way he commits suicide. So that's pretty sad. Cantor, on the other hand, he spent a lot of his life thinking about infinity, okay, and different levels of infinity, an infinity of infinities. And so it's maybe not surprising that he spent most of his time in a mental institution. Okay, so what was the situation? Let's look at the situation, the infinity situation in mathematics, pre-Cantor and post-Cantor. So pre-Cantor, it was sort of like this. So most mathematicians, I think, had this idea, and we can sort of paraphrase Gauss, one of the greatest mathematicians who's ever lived. So his idea was like infinity is nothing more than a figure of speech which helps us talk about limits. The notion of a completed infinity doesn't belong in mathematics. So what does that mean, completed infinity? So the idea of completed infinity is that you should be treating infinite objects, like infinite sets, just like any other object in math, just like any finite set. Okay? Because before Cantor, that was sort of, I guess, taboo. You could not treat infinite sets as mathematical objects. Okay? So post-Cantor, it's like infinite sets are indeed mathematical objects, just like finite sets, and we should study these infinite sets just like we study finite sets. And this is why basically Cantor is considered to be the father of set theory, because before this, there wasn't anything sort of non-trivial about set theory. Most of the things were sort of clear and trivial. But like when you add infinite sets, the idea of infinite sets, he showed that set theory is actually much more interesting than one could imagine. Okay, so let me list you very quickly some of the contributions of Cantor. So as I said, he studied infinite sets. He was the one who gave an explicit definition of one-to-one correspondence and made use of this. Although the idea of one-to-one correspondence was used before, but he was like really the one who explicitly stated it and used it. And he said that this is the right way to compare the cardinality of sets. He showed that there are actually different levels of infinity, and actually there are infinitely many infinities. He showed that the set of natural numbers, even though the set of natural numbers and the set of real numbers are both infinite sets, he said that actually the set of natural numbers is a smaller infinity than the set of real numbers. And even though the set of natural numbers is a proper subset of all the integers, he said, well, actually, they have the same cardinality. Okay, and lastly, I mean, among other things, of course, he showed that the set of real numbers is a bigger infinity than the set of natural numbers using his famous diagonal argument. Okay, and I am guessing that, like, who here hasn't seen the diagonal argument? A couple of you. Okay, so most of you have seen it, but we're definitely going to do it again because it's really, really important. Okay, so those are like a very quick summary of Cantor's ideas. Let me now tell you about the reaction at the time, the reaction of other mathematicians to Cantor's ideas. Okay, reaction to Cantor's ideas. Poincaré said most of the ideas of Cantorian set theory should be banished from mathematics once and for all. Kronecker, I don't know what predominates in Cantor set theory, philosophy or theology. Scientific charlatan. Corrupter of youth. Wittgenstein, wrong. Okay? Utter nonsense. Laughable. But there were people who actually appreciated Cantor's work, one of them being David Hilbert. And he said, no one should expel us from the paradise that Cantor has created. And to that, Wittgenstein said, if one person can see it as a paradise, why should not another see it as a joke? Okay? So this guy was really not a big fan of Cantor. And some people say this was a major contribution to his mental illness, Cantor's mental illness, because people really didn't treat him well. Okay, so let's start counting. So how do we count sets? So if A is apple, orange, banana, melon, and we say the size of the cardinality of A is equal to 4, what do we really mean by that? Okay, so we understand what we mean by it, but like, how would you actually mathematically formalize that statement? What does that mean? So what it means is that there's a one-to-one correspondence, actually, if you think about, between the sets A and the set 1, 2, 3, 4. Right? So when you're counting like apple, orange, banana, melon, you're making a one-to-one correspondence between this set and the natural numbers, 1, 2, 3, 4. Okay, so here's the picture, just like that. So that's easy. Okay, so if we have two sets now, A and B, they have different objects, or maybe possibly same objects, doesn't matter. What does the cardinality of A equal cardinality of B mean? Okay, that means that you can make a one-to-one correspondence with both of them to the same numbers, right? 1, 2, 3, 4. But really, if you think about it, why make a correspondence with 1, 2, 3, 4, skip that step, and just make a one-to-one correspondence between the two sets, right? So A equals B, when we're talking about finite sets, it means that there's a one-to-one correspondence between the sets, right? So this is basically what I just said. Okay, now let's look at three important types of functions, which I hope you've all seen before, right? So we've been talking about one-to-one correspondence, but there are also two other kinds of functions that are important. So the first one is injective or one-to-one mapping. The second one is surjective or an onto mapping. And the third one is a bijection or one-to-one correspondence. So when is a function injective? So a function from A to B is injective if no two elements in A map to the same element in B, right? So here's the picture. So no two elements in A map to the same element in B. And if there is a injection from a set A to a set B, then I'm going to use this notation. I'm going to use this notation A, this arrow with a little hook to B. That will mean that there is some injection from A to B. There's some injective map. Now, surjective map is a map A to B such that every element of B gets covered by this map, right? So the picture looks something like this. So all the elements of B are mapped. Well, there's a pre-image of every element of B. And the notation I'm going to use if there is a surjection from A to B is this like double two-headed arrow, A to B. And as you all know, a function is bijection, a one-to-one correspondence, if it's both injective and surjective. And that corresponds to a picture like this, where there's a one-to-one correspondence between the elements. And the notation I'm going to use is this, A to B, if there's a bijection from A to B. Okay? And sort of if you look at the pictures and if you think about it, for finite sets, you could really define, compare the cardinalities of two sets using this notation. You could say A is less than or equal to B, the cardinality of A is less than or equal to B, if there's an injection from A to B. And if there is a surjection from A to B, then the cardinality of A is greater or equal to B. And if there's bijection, then they're the same. So for finite sets, you can go home and check. This all works out. And we should actually, if we do define these notation of greater or equal to and less than or equal to in this way, we should do some sanity checks. Okay, for example, the size of A is less than or equal to size of B if and only if the size of B is greater or equal to size of A, right? So in our definition, that would correspond to there is an injection from A to B if and only if there is a surjection from B to A. Okay, so that happens to be correct. The size of A is equal to B if and only if the size of A is less than or equal to B and the size of A is greater or equal to B. That corresponds to this statement, right? There's a bijection between A and B if and only if there is injection and a surjection. Well, that's by definition of bijection. But you could also say, well, the second one, A is greater or equal to B, that's also the same as like there's a injection from B to A. So that also is true. Okay. And lastly, transitivity, if A is less than B, B is less than C, and A is less than C, then, well, if A is less than B and B is less than C, then A should be less than C. And you can check that that's also true. Okay, so you can do whatever check you want. Everything will work fine. Okay, one more definition. Something that we did not define is what's A less than B, the size of A less than B. That's equivalent to not A greater or equal to B, right? Which means that there's no surjection from A to B, right? Or that there's no injection from B to A. Okay, so these are equivalent things. Or you could also do it this way. You could say there is an injection from A to B, but there's no bijection between A and B. Okay? So whichever you prefer is fine. And really, Cantor's idea is that these are basically the right definitions for infinite sets as well. Okay, so that's it. Okay, so I'll see you guys next time. No, okay, so the thing is, if you check all these, if you make these definitions for infinite sets, and now you check all these sanity things like for infinite sets, they work. Okay, so like, for example, this one is called the Cantor-Schroeder-Bernstein theorem. Okay, so everything works if you check for infinite sets as well. Okay, but the really interesting thing is, like, now if you look at the consequences of this, it becomes really interesting. Okay, so this, these simple ideas translate into some interesting ideas. Okay, so now let's, for example, look at examples of equal size sets. So, as I said earlier, so the natural numbers turns out, and the integers, they have the same size. So these are the natural numbers, there are the integers. Okay, so what do you need to do to show that the natural numbers and the integers have the same size? You need to show that there's a bijection between them. Okay, and here's the bijection. So 0, 1, 2, 3, 4, 5, 6, 7, 8. I'm listing the natural numbers at the top, and here are the integers at the bottom: 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, and so on. So that's a well-defined bijection. If you want an explicit formula, here it is. Okay? So actually, if you want to show that a set S has the same size as the natural numbers, what you can do is you can list the elements of that set, make a list so that eventually every element appears in that list. Okay? So if it's listable, okay, let's call that. If the set is listable, then it has the same size as natural numbers, because that corresponds to a bijection between the natural numbers and that set. Now you should say, hold on. The natural numbers is a proper subset of the integers. And you know, if you have if A is a proper subset of B, then it must be like the size of A is strictly less than the size of B, right? So surely it must be the case that natural numbers, the size of natural numbers, must be less than the size of integers. All right, so what's going on here? So maybe it's not the right definition. Okay, maybe Cantor got it wrong. Okay, because our intuition says that this must be true. But, you know, this intuition is true for finite sets, but it's definitely not true for infinite sets. Okay? So let me try to convince you why it's not true. So let me ask you a question. If I take a set and if I rename the objects in that set, does that change the size of the set? Okay? So if I had the elements of the integers, okay, and then I just rename them. I call them like banana, apple, melon, orange, mango, whatever. Okay, and I can make up words as I need. Would that change the size of the set? No. So let's call the set F. So you agree that if I rename the objects, the size doesn't change. So the size of F should be equal to size of the integers. But now, how can you justify that the size of n should be less than the size of f? Because your claim is the size of n is less than the size of z, the integers. How could you now justify saying that the natural numbers has a smaller cardinality than this set f? You could not, okay? You wouldn't be able to justify it. Okay, and obviously bijection is nothing more than renaming, right? That's the idea. So I can rename now these fruit names back to like 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on, and get the natural numbers back. Okay, so think about that. Okay, so let's look at other examples of equal size sets. So the natural numbers has the same size as the squares. Squares being 0, 1, 4, 9, 16, the numbers that are square of another number. Okay, so S looks like it should be smaller, but it's not, right? So if we take the mapping f of n equals n squared, that's a good bijection. We can also look at the prime numbers, list 2, 3, 5, 7, 11, and so on. And these are also equal size sets. And sort of the proof is like right there, because I'm giving a list of the prime numbers, right? So whenever I can list these objects like that, that's a bijection, right? And now in this case, the bijection would be what? It would be that f of n is equal to the nth prime number. So the point of this example is that you may not always have an explicit nice formula for this bijection. Okay, but just because you don't have a formula for it doesn't mean that there is no bijection. Okay, so this is a perfectly valid bijection. Okay, so the size of n is equal to the size of A if A is infinite, and you can list the elements as A0, A1, A2, and so on, right, in a well-defined way. Okay, so here is the famous definition. So we'll say that the set A is countably infinite if it has the same size as the natural numbers. And we're going to say A is countable if A is finite or it's countably infinite. Okay? So far, so good. Now, you might, if you're a bit careful, you might ask the following question. Well, what if A is infinite, but the size of A is less than the size of the natural numbers? Right? So this definition doesn't. So in that case, it's not countable. So what do you guys think? Yeah. So there's no such thing, okay? No such set exists. And I guess you can, as an exercise, try to think why that's true, okay? So really, we can say A is countable if the size of A is less than or equal to the size of the natural numbers. Okay, let's look at some other examples. Let's look at Z times Z. So is this countable? So here's the picture of Z times Z. So the plane, the lattice, integer with integer points. So who thinks this is countable? So why? What's the bijection? Yeah?
You can go around in a spiral starting at 0, 0.
Very nice. So you could do a spiral, okay? And that's the way you can list the numbers. And you see that if you go with the spiral, eventually you will cover every element in Z times Z. Okay, so here's the list of these particular points. How about the rationals? Q is the rational numbers. Okay, so this one is interesting because you think about the rational numbers on the number line. They're dense, right? So between any two rational numbers, there's another rational number. Between any two rational numbers, there's another one. There's another one. So you could not just like take the list to be like the order in which they appear on this number line, right? Because if you take a list like that, well, between any two elements, well, I could find another one in between. Right? But it's still countable, and you can see it as follows. So any rational number, you can write it as a fraction, right? A over B for some integers A and B. So that shows that there is a surjection from z times z to the rational numbers, right? So you just map a comma b to the corresponding rational number fraction, and this way you're guaranteed to cover all of the elements in Q, the rationals, right? So that shows that this is surjection, which means that the size of Q is less than the size of z times z. But we just saw before in the previous slide, z times z, the size of that is the size of the natural numbers, right? So we know that the size of Q is less than or equal to the size of n, but it's also obviously true that the size of n is less than or equal to the size of Q, right? Because it's a subset. So the size of n is equal to the size of Q. Okay? Any questions? Yeah.
So if an infinite set is a subset of another infinite set, we know that it is less than or equal to
If it's,
the cardinalities, I mean?
yes, because you can just, there's always a surjection.
Okay, right.
Yeah. All right, so now let's look at more like computer science-y sets, like 0, 1 to the star is one of our favorite sets, right? So this is the set of finite length binary strings. So is this countable or not? So what do you guys think? Yes. Why? Because, well, okay, so let's look at the elements of the set. So we can write it like this: the empty word, then 0, 1, then the words of length 2, then the words of length 3, and so on. And there you go. That's your listing. And that basically shows that there's a bijection between n and 0, 1 to the star, right? So you start with the empty word, then you list all the words of length 1, then you list all the words of length 2, then you list all the words of length 3, and so on. How about sigma star, where sigma is some arbitrary alphabet? Okay. Where sigma is, let's say, a finite set. Same idea, shows that this is countable. Actually, we're gonna, here's a CS method to show that a set A is countable. Okay. In other words, showing that the cardinality of A is less than or equal to than the cardinality of n. So the CS method is to show that the cardinality of A is less than or equal to the cardinality of sigma star. Okay? Because the sigma star has the same cardinality as n, so we can do this if we want to show that it's countable. And this is equivalent to saying that there's a surjection, there's an onto map from sigma star to the set A. Okay? Now you could also show that there's an injection from A to sigma star, but usually it's easier to show that there's a surjection than to show there's an injection. Because to show a surjection, all you have to do is show a map that covers all the elements of A. Okay, that's it. Okay, so let's see the CS method in action now. Okay, so is Qx countable? So what is this set? This set is the set of all polynomials with rational coefficients, with x being the variable. Okay, so this set is going to be countable, and we can show it using the CS method. So take sigma to be this set, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, the variable x, plus, minus, multiplication, division, and exponent. Okay, and now it's easy to see that every polynomial can be described by some finite string over sigma. Right, so for example, take this polynomial. Obviously, this polynomial corresponds to a string in sigma star. So that shows that there is a surjection from sigma star to Qx. Now, not every element in sigma star is going to correspond to a polynomial, right? But that's okay. So what you can define, you can map those elements to whatever you want. That doesn't matter. Okay, but the important thing is that every element of Q of X will have a preimage. Okay, any questions on this? So it seems like every set is countable. Okay, but Cantor says, you know, that would be kind of boring. So let me now state Cantor's theorem. Okay, so Cantor says that for any non-empty set A, the size of A is strictly less than the size of P of A, which denotes the power set of A. Okay, so let me remind you what power set is. So if S is the set 1, 2, 3, the power set of S is the set of all subsets of S, right? Now, if S is finite like that, what is the size of the power set of S? It's 2 to the size of S, right? And a nice way to see this is that there's actually a bijection. There's a nice bijection between the power set of S and 0, 1 to the size of S. So 0, 1 to the size of S is, of course, binary strings of length S, the size of S. So what's this bijection? Well, if you take a set S1, 2, 3, and say, okay, what does the string 1, 0, 1 correspond to? Well, it corresponds to the subset 1, 3 because 1 is in the set, 0 is not in the set, and 3 is in this set. So say again. 1 is in the set, 2 is not in the set, 3 is in the set. If you said like 0, 0, 0, that will be the empty set, right? So for each element, you have two options. You can either put it in the subset or not put it in the subset. Okay. So that's a very often there's a very useful perspective. Sometimes it's very useful to think of subsets of a set as binary strings. Okay, so Cantor is saying the size of A is less than the size of P of A. So that's of course trivial when A is a finite set. But of course, the real contribution here is that this is also true when A is an infinite set. So in particular, if I were to take A to be the natural numbers, that would show that the size of the natural numbers is strictly less than the size of the power set of the natural numbers, right? Which shows that the power set of n is not countable. Okay. And why stop there, right? So the natural numbers, the size of natural numbers is smaller than the size of the power set, smaller than the power set of the power set, smaller than the power set of the power set of the power set, and so on, right? So really what Cantor is saying here is that there is an infinity of infinities. Okay, and to that I guess Wittgenstein says, all right, so let's now do the proof by diagonalization. Okay, so this is the famous proof by Cantor. It's a very important proof, so let's go over it one more time, even if you have seen it before. Okay, so we're going to do this, if I can do it. Oh, there you go. So we're going to do it by contradiction. So assume that for some set A, the cardinality of the power set is actually less than or equal to the set A. Okay? What does that mean? That means that there is a onto map surjection from A to the power set A. Right? So let's call this surjection F. Okay, here's an example. Okay? Let's say the set A was the natural numbers. So we're assuming there's a surjection from the natural numbers to the power set of the natural numbers. So let's say, we have the elements of the natural numbers on the left. I guess there I'm not including 0 in the set, but that's okay. And they are mapped to some subset of the natural numbers. Now we're going to define a set S as follows. The set S is going to be all the elements in A that is not contained in the set that it's mapped to. Okay, so for example, when I look at the number 1 and I want to decide, is 1 in the set S, I look at the set that it's mapped to, 379. 1 is not in the set 379, so I put 1 in S. I go to 2, I look at whether 2 is contained in the set that it's mapped to, 2, 5. It is, so I do not put 2 in the set S. I go to 3, 3 is contained in 1, 2, 3, so I do not put 3 in the set S, but 4 is not contained in the set 1, 2, 3, so I do put 4 in the set. So this S for this particular example looks like 1 and 4 and possibly other elements. Okay, and obviously S is a subset of A, so it is in the power set. It's an element of the power set A, which means that, and also, recall that F is a surjection, right? F is an onto map. So that means that there is some element in A, let's call it small s, that maps to capital S. Right? There must be. Because this F, as we assume, is an onto map. Right? And S is a subset, is an element of the power set. Okay. But here is the thing. So this is a contradiction. Okay, so why is this a contradiction? So to see that it's a contradiction, let's look at whether S, the small s, is contained in capital S or not. Okay. So how do we determine if an element is in capital S or not? We said, like, for 1, we looked at whether 1 is contained in 379. If it's not, then we put it in S. 2 was contained in 2 and 2, 5, so we did not put it in S. But now if you come to S and we say, if S is in capital S, right, then we would not put small s in capital S. Right? And conversely, if S, small s, was not in capital S, then we would put, actually, small s in capital S. Okay, so that's the contradiction. So if you said, if S is not in S, well then, by definition, we have to put small s inside capital S. And if small s is in capital S, then by definition, we cannot put small s in capital S. And that's the contradiction, and that's the proof. Okay, so then you wonder, why is this called a diagonalization argument? Okay, so let me show you why this is called a diagonalization argument, showing it with this example. Okay, so we're back to natural numbers. Let me build the following table, okay? So the table, the columns are labeled by the natural numbers 1, 2, 3, 4, 5. And the rows are labeled by f of 1, f of 2, f of 3, f of 4, and f of 5. And then I'm going to fill this table as follows. I'm going to say, okay, is 1 contained in f of 1? No, it's not. Then I'm going to put a 0 in the corresponding position. Is 2 contained in f of 1? No, so I'm going to put a 0 in the corresponding position. Is 3 contained in f of 1? Yes, it is, so I'm going to put a 1, and so on. So I filled this table up like this. Now, as we said, we construct this set S now, capital S. And as we said, it has to be in this table somewhere, right? Because it's an onto map. So there must be some small s that maps to S, so f of s equal to capital S. But now let's look at how we actually defined capital S. Okay? What we did is, to determine whether 1 should be in capital S or not, we looked at whether 1 was in f of 1. If it's not in f of 1, then we said, okay, we're going to put 1 in S. Okay? Then we looked at whether we should put 2 in S or not. Well, 2 was contained in f of 2. There was a 1 there, so it's not going to be in S. So we're going to put a 0 there. So as you see, whatever the diagonal element is, S has the opposite value. Okay? But now that's the contradiction, because observe that S cannot be in this table. Why? Because S cannot be f of 1 because it differs from f of 1 in the first column. It cannot be f of 2 because it differs from S in the second column. It cannot be f of 3 because it differs from f of 3 in the third column, and so on. So it cannot be in this table, but it has to be in this table. And that's the contradiction. So in a sense, we are defining S so that S cannot equal any f of A in this table. Okay, and this is why it's called diagonalization argument. Now, if this makes you a bit uncomfortable, let me just say that it's okay. Like a lot of people find this argument uncomfortable at first. I think there are even people today that don't really accept it. But, you know, almost every serious mathematician does accept this argument. And I don't know exactly, I cannot pinpoint exactly what it is that makes people uncomfortable about this argument. So if you are able to express why you're uncomfortable about this argument, send me an email. I'll be happy to read it and learn about it. Okay. So we've seen that the power set of n is more than, the size of the power set of n is more than the size of n. So that's not supposed to come up there, but okay. So a set A is basically uncountable, so it's a definition, if it is not countable, right? So that means that the size of A is more than the size of n. And these are some examples that we've seen already. So let's look at some other examples of uncountable sets. So for example, let's look at 0, 1 to the infinity. So what does that set mean? So it's the set of binary strings of infinite length. Okay, so 0, 1 to the star was the set of binary strings of finite length. So this one is a set of strings of infinite length. So for example, it can have elements like this. So maybe the all 0 string that goes to infinity, the all 1 string that goes to infinity, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0 that goes to infinity. And as you can guess, 0, 1 to the infinity is uncountable, meaning it has size larger than the size of the natural numbers. So why is that the case?
Just a quick question.
Yeah.
Are we allowed to use this infinity notation?
Are you allowed to use this infinity notation? Yeah.
Okay.
Sure. So anyone? Why is this? Yeah.
So suppose that you have a mapping from natural number to a binary string so that you can just lay them out and then flip every
Right, so you're describing the diagonal argument. Good. So you could do it by diagonalization. But like we've already sort of done this. Okay, so if you look at this, 0, 1 to the infinity, there is a clear bijection between the power set of n and 0, 1 to the infinity, right? Just like there is a bijection between 0, 1 to the s and the power set of s that we discussed. Right? So for example, the all 0 string corresponds to the empty subset. The all 1 string corresponds to the natural numbers. 1, 0, 1, 0, 1, 0, 1, 0, that corresponds to the even natural numbers and so on. So that's a bijection. And recall 0, 1 to the star was countable. And 0, 1 to the infinity is uncountable. Okay? But as you said, we can actually do this directly using a diagonal argument. Okay? So suppose 0, 1 to the infinity is less than the size of n. So there's a surjection from the natural numbers to 0, 1 to the infinity. Let's look at the following table. So the fact that there's a surjection from the natural numbers to 0, 1, infinity means that I can list these elements of 0, 1, infinity like this. Okay, so 1, let's say, gets mapped to this string, 0, 1, 0, 0, 1, 0, 0, and so on. 2 gets mapped to that one, and so on. And since it's a surjection, every element of 0, 1 to the infinity must be in this table. But now let's look at the diagonal. Okay, let's flip the elements of the diagonal, and let's build this string. 1, 0, 0, 1, 0, and so on. By construction, this is not an element, cannot be an element of this in this table. But this mapping was supposed to be a surjection. So this element was supposed to be in this table. Okay? So that's a direct diagonal argument. So this cannot appear in the list. So here's another fact that you probably know. The real numbers are uncountable. Okay? In fact, if you look at the real numbers between 0 and 1, that's also uncountable. And this is now a simple exercise. Like after what I've shown, this is really a simple exercise. So appreciating the diagonalization argument. So I would say, if you want to really appreciate something, try to break it. Okay? Now this is not true for everything in life. So don't try it for everything in life, but it's a good thing to try when you have a proof like this and you want to really understand how the proof works. Try to break it in the sense that, as an exercise, try to try to apply it to the natural numbers, the diagonal argument. Try to apply it to 0, 1 to the star. Try to apply it to a countable subset of 0, 1 to the infinity. Okay, and see, it has to fail, right, when you try it. See why it fails. Okay, I think that's a useful exercise. All right, so before I end this section, I want to say just make a little remark here. So here's a question. Is there a set such that the size of n, the size of S is between the size of n and the size of P of n? Anyone? No. Okay. We don't know. Okay. So this is called the continuum hypothesis. And it was a conjecture so that no such set exists. It was conjectured by Cantor himself. And he spent a lot of time trying to prove this. But he was not successful. And I guess that's another reason why he ended up in the mental institution. But, poor him, no one could tell him that there was a good reason why he was not able to do it. And actually, this is also Hilbert's first problem. If you remember the first lecture, Hilbert provided 23 problems to the mathematicians. This was the first problem, actually, continuum hypothesis. But, we'll probably talk about this later, perhaps, probably, yeah. So, I'll just say that it turns out that the continuum hypothesis is independent. So you cannot prove the continuum hypothesis using ZFC from the axioms of set theory. You cannot prove that it's true, and you cannot prove that it's false. So in that sense, it's called independent of ZFC. Okay, but we'll probably talk about it later. Okay, so now we go on to applications to computer science. So all these things that Cantor developed has very profound applications in computer science. Okay? Because it answers the most basic question in computation that you can ask. Are all problems computable? Right? So that's like the most basic question you can ask. Okay? And it turns out that most problems actually are not computable. Okay? How do you show that? Well, you just count. Okay? That's it. Okay? So you say, for any Turing machine M, if you look at the encoding of M as a string, right? So that's clearly in sigma star, right? And whenever you can encode the elements of a set using sigma star, we can apply the CS method and show that this set is countable. Okay, so the set of all Turing machines is countable. What about the set of all problems? Well, a computational set of all computational problems or languages, right? Let's say the set of all decision problems equivalent to the set of all languages, where L is a subset of sigma star, is of course the power set of sigma star, right? But the sigma star has the same cardinality of n, the natural numbers, so this is like the power set of the natural numbers. This is uncountable. Right, so we have, so basically, the countable, so the Turing machines, the number of Turing machines, or the number of, in other words, the number of problems that are computable is just a drop in the ocean of all computational problems. Okay, so that's like a big negative result. Okay, so you might say, well, that's really bad, but maybe all uncomputable problems, all these problems that are uncomputable, they're not interesting, right? Because after all, whatever you try to compute, well, you sort of write a program for it and you sort of seems like you can compute it, right? It doesn't seem like you come across these uncomputable problems. But in fact, this is not true, and that there are some very interesting problems that are uncomputable. Okay? So one of them is called the halting problem. So let's say that you're a person, you're Neo, you're the one, you're working at Matrix Inc., and your boss is Morpheus, and he has a problem. He says, Neo, debugging Trinity's code is taking too much time. I think she keeps writing infinite loops. And then you say, you're Neo, you say, of course, I'm the one, I can fix anything. Say, the first thing I'm going to do is I'm going to write a program that checks for infinite loops. Okay? I'm just going to first do that, and then we'll take it from there. Okay, and then how do you write such a program? And then Turing says, you know, you might be the one, but this is actually impossible to do. Okay, this problem is uncomputable. So here's the theorem. The halting problem, the problem of detecting whether a given program halts or not, is uncomputable. And I'm going to now show you a proof of this. And the proof method I'm going to use is not really very popular among theoretical computer scientists. So the proof method I'm going to use is proof by Python. Okay. So first, let's define the problem. So the halting problem is the following. So you're given two inputs, a Python program file, and an input to that program. So this halting program is like really like a, in some sense, an interpreter compiler kind of thing. Like it takes the code of another program, and then it's supposed, and it also takes an input that's supposed to be an input to that code, And it checks, it says it's supposed to output true if the program, if the given program, halts for that given input, and false otherwise. Okay, so simply we want to write this halting function. Okay, so again we go by contradiction, right? Suppose such a program exists. Okay, so assume such a program exists. So I was able to write some Python code that established this. Okay, we'll call it the halt function. It takes two inputs, program and input to program. Both are strings, right? And it returns true if program halts when run with input to program, and false otherwise. Okay, suppose this exists. Now let's look at, I'm going to define another function in Python, okay, that uses halt as a subroutine. Okay, and what does it do? So it takes a program as input, okay, and then it calls this halt function with program, as the input being program comma program. So it's really checking if the given program halts when it's given its own string as input. If it does halt, then this part is basically an infinite loop. So this Turing goes into an infinite loop. Otherwise, if it does not halt, it returns none, which means that Turing halts. So in some sense, it's doing the opposite of what halt is saying, right? If the halt is saying, yeah, program halts when run with input program, then I'm going to go into an infinite loop. But if it does not halt, it's in an infinite loop, then I'm going to halt. Okay, and then this leads to a contradiction. Because think about now what happens if I call Turing and give its code as input. What happens, right? So substitute Turing as program here, okay? Now if halt Turing, if this returns true, well then I go into an infinite loop, so Turing does not terminate. But if on the other hand, halt Turing returns false, then I do terminate. Turing does terminate. And that's contradiction. Right? If it halts, it doesn't halt. If it doesn't halt, it halts. Okay, and that completes our proof by Python. Now, you could take this proof, basically word for word, and then replace Python with a Turing machine and get the same proof. Okay, but before actually I go to that, this is also called a diagonalization argument, by the way. Okay, so this is like extremely similar to Cantor's argument. Why is that? Let's see it very quickly. So again, here's our program Turing, right? This function Turing we had. Let's look at the following table. Okay, on the left we have all possible Python functions listed here, right? So that's a countable set as we saw, right? Or set of all Python functions. A Python function is an element of sigma star, can be encoded using sigma star. And on the top, I have the encodings of those functions. So the function f1 as a string, the function f2 as a string, and so on. And the way I'm going to fill up this table is as follows. If I give the string f1 as input to f1, if it goes into an infinite loop, I'm going to put an infinity sign. But like if f1 given the string of f3 halts, then it's a h. Okay, so infinity of h like that. And then you say, well, this Turing program, well, it's an honest to God Python program, right? It must be in this list somewhere here. But let's look at what Turing does. When given input f1, the string f1, it checks whether f1 halts when given f1. So it looks at this. If it's an infinite loop, then Turing will halt, right? Then for f2, well, when f2 is given as input to f2, it halts, then it will go into an infinite loop and so on. So it's taking basically the diagonals of this table, flipping them so that it cannot be in this table. Okay, so that's why it's called diagonal argument. Okay, so now here's the proof by theoretical computer scientists of the same thing. So you first formally define what your language is, halt. So your language consists of these strings m comma x, where m is a Turing machine that halts on input x. And then you say, suppose m halt decides halt, right? So m halt, the Turing machine m halt, corresponds to the halt Python program that I described. Consider the following Turing machine. Let's call it m Turing, and m Turing corresponds exactly to the Turing function that I described. And here is the description of m Turing. Treat the input as the encoding of a Turing machine. Run m halt with the input m comma m. If it accepts, go into an infinite loop. If it rejects, accept. So flip what that does. Now let me just say here, let me make a comment here. So when we ask you to give a Turing machine that does a certain task, there are various ways you can go about doing that. The first way you can go about doing that is you can give the state diagram and give all the details of the Turing machine, okay? And sometimes, like in the homework, we are going to probably ask you to do that. But if we don't explicitly say give us the state diagram, then this level of detail is usually enough. Describing in English what the Turing machine does, okay? Just like here. And here's the picture representation of exactly that thing. So this is the m Turing machine. It takes the encoding of m as input. It runs m halt on that, and it flips sort of the answer. Okay, and then you ask what happens when the encoding of m Turing is given input to m Turing, and that leads to a contradiction, just like the contradiction that we've seen before. Okay, so I'm skipping over the details here because it's the same, exactly the same proof. Okay, so you might say now, so what? Okay, so first of all, there's no debugger program that we can write, right? So that's bad news, because that would have been pretty useful. Another thing is let's consider the following program. So take a look at this program. So the question is whether this program halts or not. So what if this program halts? What does that mean? Right, so this is related to Fermat's last theorem, right? What does Fermat's last theorem say? There is no integer solution to x to the n, y to the n, x to the n plus y to the n equals z to the n, right? For n greater than 2. Now, if this program halts, this is trying to find a solution, by the way, right? If this program halts, then we have a solution. If it doesn't halt, then we don't have a solution. So we get an answer to Fermat's question. And Fermat's last theorem is like one of the most remarkable theorems in all of mathematics. And as a side note, I'll say you should all read this book about Fermat's last theorem. It's quite fascinating. Okay, so what else? So what? Now, using the fact that the halting problem is undecidable, we can actually show that other interesting problems are also undecidable. And we do this via reductions, what we call reductions. And I'm gonna quickly show you reductions in a few moments. Okay, so for example, using this idea of a reduction, we can show that the Entscheidungs problem is undecidable. We can show that Hilbert's 10th problem is undecidable, and many other problems. Okay, and I'll say briefly a few words about these at the end of the lecture. But also, the way I like to think about this, actually, I also like to think that this maybe says something about the universe we live in as well. So you could say, well, if we had different laws of physics, maybe we could come up with different computational devices, and then maybe, you know, every problem could be computable, or the halting problem could be computable. Okay, so maybe this says something about the inherent limitations of our universe. So here's like a very interesting question, an exercise for you. Can you come up with like sensible laws of physics such that the halting problems becomes computable? I think that's a very interesting question. Okay, so now let's show some other uncomputable problems. And as I said, we're going to do this using this idea of a reduction. And this concept of a reduction is a very central idea in computer science. Okay, so this idea basically allows us to compare the difficulty of problems. Okay, now the difficulty is going to differ based on context. Okay, right now what we're interested in is decidability, computability versus undecidability or uncomputability. Okay, but later on in the course, we're going to also look at reductions in the context of computational complexity. Okay, like say running time. Okay, so what we want is to be able to define A less than or equal to B, some notion of A less than or equal to B for two computational problems A and B. Okay, and we want the meaning of this to be that B is at least as hard as A with respect to decidability. Okay, so B is at least as hard as A. And more precisely, what we want is that if B is decidable, then A should also be decidable. Right? Because B is decidable, A is a simpler, presumably a simpler problem, so A should also be decidable. And that's equivalent to saying that, of course, if A is undecidable, then B should be undecidable, right? Because B is supposed to be at least as hard. Okay? So here is a definition that does the trick. So we're going to say that A is less than or equal to B with a T subscript. T is for Turing. So A reduces to B, or A Turing reduces to B, if it's possible to decide A using an algorithm for deciding B as a subroutine. Okay? So suppose that you had a subroutine that solved B for you. Then using this subroutine, you could come up with a decider, an algorithm for A. Okay? So note that, you know, this definition satisfies the condition that we were looking for. If A reduces to B in this sense, then B decidable implies A decidable, and A undecidable implies B undecidable, right? Just by definition. Okay? Just by definition, if B is decidable, A, there is an algorithm that solves A. But that means that if I could find a problem B such that the the halting problem reduces to B, that would imply that B is not decidable, right? So if I could solve the halting problem using a subroutine for B, then that would make B undecidable. Okay? So he's in, yeah.
Wait, so like, for the example you gave where if B is decidable, then that implies A is decidable. How do you know that A doesn't need like some other subroutine C that like isn't decidable?
Well, if you're able to describe a procedure that does not require you to solve some other undecidable problem,
okay,
right?
So just with B.
Just with B.
Okay.
You can do other stuff, of course, but it has to be like decidable stuff, right? It's not, you're not solving some other crazy, yeah. So here's an example of this. Let's look at this language accepts, which is the set of words m comma x, where m is a Turing machine that accepts x. So this is undecidable. Let me make a few observations here. So if m comma x is in the language, what does that mean? That means that x leads to an accept state in m, right? Obvious. Now, here's the other thing though. If m comma x is not in the language, that does not necessarily mean that x leads to a reject state. It might lead to a reject state, or it might go into an infinite loop. Okay, because in that case it doesn't accept. Okay? And also observe that, since we're going to try to reduce halt to this problem, if m comma x is in halt, m comma x is in halt if x leads to an accept or reject state, right? That it does not go into an infinite loop. So, okay, so now with this in mind, let's do our reduction. Okay, we're going to show that accepts, halt reduces to accepts. We're going to do the proof by picture. So we want to come up with this algorithm for mhalt using the fact that we have an algorithm that solves accepts. What are we going to do? Okay, so it's quite simple. We're going to first feed this input mx into maccepts. Right? If it accepts, that means that x leads to an accept state. So it halts. So in that case, we can accept because it halts. But if it rejects, there are two possibilities. Either x led to a reject state, or it led to an infinite loop. But we don't know at the moment which one is which. So we have to be able to detect that. So to detect that, what we do is we take m. So here's a little another subroutine. Take m, and we just reverse the accept and reject states in m. Okay? We flip the accept and reject states, and then we're going to now run x with m prime and see if it accepts. If it accepts, that means that x leads to an reject state in m. Right? So in that case, it halts, and that's accept. But otherwise, if it rejects, at this point, we know that x did not lead to a accept state, and we know that x did not lead to a reject state, so it must be an infinite loop. So in that case, we reject. Okay, so that's proof by picture, but if you're asked a question like this, you should be more formal about it, of course, and write down everything nicely. So this is basically the way you would write it down, but it's exactly the same thing. So I'm not going to go over this, but you can read it by yourself. Yeah.
You pretty much always use the halting problem in your reduction, or are there other like unsolvable problems that are common to use?
So that's a good question. So in some sense, it comes to the question, the thing that I'm going to come here. You could prove directly by diagonalization that some other problem is not uncomputable. Okay, and let me also say the following thing. So reductions are transitive, right? So if A is less than or equal to B and B is less than or equal to C, then that means A is less than or equal to C. So it follows directly from the definition, which means that, you know, now if I want to show some other language is undecidable, you know, I could do a direct reduction from halting, but I could also do a reduction from except now. Right? So for example, this one, MT, M is a Turing machine that accepts no strings, is undecidable, and it suffices to show that excepts reduces to empty, because I've just shown that halt reduces to excepts. So that would imply that halt is less than or equal to empty, reduces to empty. Right? So in this way, you can indirectly show that halting reduces to another problem. But as I said, you could also take a problem and directly apply a diagonalization argument to. So this is probably an exercise or a recitation problem or some homework problem. One of the three. Here's another one regular. I'm going to just skip that. Interesting observation, though, here is that we are showing a negative result that there's no algorithm, by showing a positive result, that there's a reduction, that there's an algorithm. A reduction is nothing but an algorithm, right? And that's quite nice, because our brains are better wired to come up with algorithms than to show that there is no algorithm. Okay, so in the last 1-2 minutes, let me just tell you that about some undecidable problems not involving Turing machines, because the examples we've seen so far seems like they all involve some, you know, Turing machines, and they might not feel so natural to you. But I told you, right, by reduction you can show that Entscheidung's problem is undecidable. And actually, Alan Turing showed this in his original paper, in the paper that he introduced the notion of a Turing machine. So in a sense, computer science was born aware of its limitations. Okay? And I don't know if you can say that about any other field. Hilbert's 10th problem, right? This is also, this was shown much later in the 1970s because this was much harder. Again, by reduction from the halting problem. So this is like determining if a given multivariate polynomial with integral coefficients has an integer root. So if we ask the question whether it has a real root, actually this is decidable, proved by Tarski. And if you ask, does it have a rational root, no one knows if that's decidable or not. There's another problem, post-correspondence problem, that you're going to study in the recitation. I guess since I'm out of time, I'm going to skip this, but you will study this problem in the recitation anyway. This is undecidable, proved by 1946. So really, okay, so we've seen that most problems are undecidable, and we've seen that some very interesting problems are undecidable as well. But all hope is not lost. So actually, most interesting problems, most problems that interest us are decidable. Okay, so the next question will be, okay, if it's decidable, what's the next important question we can ask about the problem? And that will be the computational complexity of a problem. Right, thank you.